Welcome everyone to today's PCS IBS seminar. It is a great pleasure.
I think it's disconnected. Can you hear me? Hello, can you hear me? Oops, I think it's disconnected. Hello?
I can hear very well, Pilkyung. So there's a problem with maybe.
Yeah, I think it was temporary problem.
Oh, you
I think now it's fixed. Yeah.
He then disappeared. Now he's back.
Okay.
Now it's back.
Okay. It seems I'm having some technical issues, so I apologize. I don't know if you've heard anything from before. I'll say again. So welcome everyone to today's PCS IBS seminar. It is a great pleasure to have with us Professor Pilkyung Moon. And I would like to invite our scientific host, Hichul, to introduce our speaker. Please, Hichul.
Yeah, thanks, Tilam. Yeah, thank you for your joining this seminar. Yeah, it is very nice opportunity to have Professor Pilkyung Moon with us. He is affiliated in New York University, Shanghai in China. He did get the degree of PhD in Department of Material Science and Engineering in SNU in Korea. And yeah, he did an intern researcher in KIST, Korea. And then 2010, he moved to Japan as a postdoctoral researcher in JAIST. And then got an assistant professorship in Dodecagonal University 2011. And then 2013, he came back to Korea as a research fellow in KIAS, Korea. And 2014, now he is an assistant professor in New York University, Shanghai, China. Actually, he has a quite impressive publication record in Graphene. He is always his name, there is his name in most important papers related to the bilayer graphene, such as Hofstadter butterfly in Moire superlattices and dodecagonal graphene crystals. Today he will give us a talk. The title is Physics in, sorry, I cannot see the title. Oh yeah, Physics of incommensurately stacked two-dimensional atomic layers. Okay, let's welcome speaker.
Thank you very much. Yeah, glad to meet you, and thank you for inviting me to the very interesting seminar. So I would like to very briefly introduce the physics of incommensurate atomic layers, mainly focusing on graphene quasicrystal. But I will mainly focus on introduction. And if you are interested in the actual, more detailed formula, please ask me anytime, even during the seminar or after the seminar. Okay, before I start, let me very briefly introduce our university. Actually, this is the most frequently asked question. New York University has 3 campuses in New York, of course, and Shanghai and Abu Dhabi. These are the main campuses which grant the degree to students. And besides these 3 campuses, we have 12 sites, study away sites that provides a course for 2 or 3 disciplines. So students mainly study in either of the 3 campuses, but study away at least one of the sites for 6 to 12 months before they graduate. Okay, so let's start our talk. In the first part, I will very briefly introduce the Moire superlattice, what it is, and what is the interesting property we expect. But I will mainly focus on the graphene quasicrystal because this is much newer topic. Okay, so what is Moire superlattice? Since the discovery of graphene in 2004, many of its cousins, such as hexagonal boron nitride, transition metal dichalcogenides, and phosphorine have been discovered. These materials not only provide interesting properties by themselves, but also serve as a building block to make a new kind of superlattice, Since the intralayer interaction is very strong, but the interlayer interaction is very weak, we can easily attach or detach the layers. So we can make a huge variety of superlattices, and by stacking atomic species, by controlling the atomic species and stacking sequences. However, it should be noted that whenever atomic layers are stacked incommensurately, there always arises an extra periodicity along in-plane direction. Why this happens? Imagine what happens if we stack two layers of a periodic pattern. If the two layers have the same period, then we get the overlaid pattern also has the same period. But if there is difference between the lattice period or lattice orientation, there arises an extra periodic pattern, which we call Moire interference pattern. We can easily find Moire phenomena in many macroscopic world phenomena. For example, when we see two stacks of a rectangular pattern, we can see extra periodicity with much longer periodicity. The same happens in a microscopic system. For example, if we stack two layers of graphene and twist them by an arbitrary angle, we get an extra periodicity, which we call Moire superlattice period. The period of a Moire pattern varies with the rotation angle between the layers. And it was actually verified in a STM, the scanning tunneling microscope image. As the rotation angle decreases, the Moire period gradually increases. One of the most important property of Moire superlattice is that their period can be much longer than any existing the conventional materials in nature. It allows us to explore the physics far beyond the limit of conventional materials, such as Hofstadter's butterfly. Okay, so how can we describe the physics of Moire superlattice, the electronic structure? Since the unit cell is very large, there can be more than 10,000 atoms in a unit cell. So although we can calculate it by using the conventional tight binding method, but it's not very feasible to do it by density functional method. Instead, we developed a continuum model by coarse grading method. As you can see, the local atomic configuration of Moire pattern varies from AA-like stacking, where red and black hexagon shows the unit cell of upper and lower layer. AA-like stacking, or BA-like stacking, or AB-like stacking, or the intermediate configuration in the unit cell, as the position varies in the unit cell. The continuum model makes ignore the complex local configuration, but replace them with a simple potential that can reproduce the potential of AA stacking, BA stacking, and so on. So various groups developed the continuum model with various approaches, but their results are almost the same. Unlike other groups, we developed the method from the tight binding description and Bloch function. And yeah, the results are almost the same. So the Hamiltonian looks like this. The diagonal component are just the intralayer interaction of graphene. The interlayer interaction looks like this. Here, A, B shows the sublattice index of upper and lower layer, and U0 is the strength of interlayer interaction. G1M, G2M are reciprocal lattice vector of Moire superlattice, and R is the position in the unit cell. If you put R equals 0 to this equation, you can see that the interlayer Hamiltonian clearly reconstruct the Hamiltonian of AA stacking. If you put R for appropriate position, then they all reproduces the potential of BA, AB, or intermediate configuration. So this effective model clearly describes the very core interaction in Moire system, and it's much cost efficient. So I plot the band structure of twisted bilayer graphene with various rotation angle by using tight binding model and effective model, and they are very consistent with each other. As the rotation angle decreases, the Fermi velocity, the slope continuously decreases and even completely drops to zero at specific rotation angle. This is what we call the magic angle of twisted bilayer graphene. And recently, superconductivity and correlated insulating phase have been discovered. Yeah, I show the unique selection rule in twisted bilayer graphene. In many condensed matters, the strongest absorption occurs between the states having the highest density of states. But I show that from analytically show that the transition between the highest density of states are completely forbidden by the lattice symmetry in this system. Instead, the peak arises from the transition to other states. And actually, I like this result. The Moire superlattice has two different periodicity. One is the period of Moire pattern, and one is the period of exact lattice matching period. In many condensed matter system, the physical properties are mainly dictated by the exact periodicity. But in a Moire superlattice, we show that the physical properties are mainly given by the Moire period. The exact period also affects some physical properties, but it's almost negligible. And
I'm sorry,
sure.
Pilkyung. What do you mean by exact? So you
exact.
Yeah, but what exactly do you mean by exact?
Okay, so let me share another. Wait a moment. Wait a moment. I didn't prepare. Okay. Wait a second. Yeah, here you go. Share the screen. Okay, can you see the screen? Yeah. Yes. As rotation angle decreases at specific rotation angle, you can see. It's much better to. Okay, Moire superlattice have two different periodicity. One is the period of Moire pattern, which I plot in red lines. You can see from far distance, you can see this red line shows some kind of periodicity. But a closer look at this, you can see that the lattice configuration at this point, origin, is different from the lattice configuration at this point, right? So this is not the periodicity in a conventional sense. Instead, the exact periodicity occurs when the lattice configuration exactly matches with that of the origin. So we have.
So what is that periodicity compared to the length scale by the Moire pattern? So are these larger? That's what you say, or are they actually infinite? What?
Yeah, only at specific rotation angle there exists the exact periodicity. So at most rotation angles, such exact periodicity does not occur. And at most rotation angle, there always a Moire period. And the exact periodicity, if exists, it's always integer multiple of Moire pattern. We can easily prove this. I think the same happens in a one-dimensional chain with two different periodicity. You can find the exact matching lattice matching point, and or the moire-like pattern.
Yeah, I mean, I'm just wondering. So what you tell is that it's the mightiness of the irrational over the rational numbers, basically. But how do I define this Moire period? You said by just looking at it, or is there some?
We can. I could define it. So at first, I defined this as the, how can I say, the registry, relative phase or the relative location between the lattice. So although, for example, although this point does not look exactly same as this point, but the relative position in the unit cell of the upper layer and lower layer are exactly same.
Can you use a pointer?
Could you say that again?
Can you use a pointer, please? Because you say this
Oh,
point and that point, and we don't know which.
Oh, I see. Wait a moment. How can I annotate?
I think there is a pointer, but it's a very hard to see.
Okay, so let me. Yeah. Can I let
something moving on the screen?
Okay, I see. Yeah. So this is the origin. Can you see this?
Yes.
And this is the origin. This is the Moire point. And yeah, I should bring the tablet, but let me briefly introduce. How can I? Wait a moment. New share and whiteboard. Yeah, in a one-dimensional system, for example, I'm sorry, I do not have a tablet now. So one-dimensional system with different periodicity. Yeah, we cannot, even if there is no exact periodicity, we can define the Moire period. What I define the Moire period at first stage, the model one is that, so if the two lattices are exactly matching, then it's of course the matching point. But even if it does not match, the relative phase, for example, this point is half the unit cell, and this point is half the unit cell. If this point and this point matches at somewhere, then that would be the Moire period. At that point, although there is no atom at that point, but the relative phase matches at that point. Actually, electrons are described by the wave vector. So this is the valid description of the periodicity in the momentum space. However, later in the model 2, the next model, I clearly described by using the momentum space tight binding model. But I think
sure, Pilkyung, let me ask again. So in this 1D case, basically, yeah, I can imagine that I can design some quasi-periodic function with two periods and then define some kind of approximate periodicity, even though I have an incommensurate ratio of the two periods. But
yep.
But that really, I would say, depends on how my question is whether that depends somehow on my taste, on my choice of what I like to be in approximate periodicity. Because when you show these Moire patterns, they seem to jump into the eye, so to say. I really see them, and still it seems that their definition is something vague. But maybe this is not so vague as it seems. Is there something more mathematical, more rigorous, which?
Yeah, it's there is a rigorous definition. Actually, I defined this using the momentum space. So the difference between the momentum space, for example, the reciprocal lattice vector of layer 1 and reciprocal lattice vector of layer 2, and that difference makes the Moire pattern. You can easily imagine this from the Moire pattern is nothing but the interference pattern. And when you combine sine wave of frequency f and sine wave with frequency f prime, you can see there would be the how can I say there occurs a very long periodicity with f prime f minus f prime over 2, right?
Okay.
Maybe.
Thank you.
I mean okay, so I will explain this in the later part, not later, but after the presentation.
Thank you.
I'm talking about I'm talking about
excuse me, Professor Moon, we have another question from Sung Jong.
Sure.
Sung Jong, please unmute yourself.
I'm just wondering what the you used like effective 2x2 effective Hamiltonian, right? So
Yes.
what are the bases of that? What do the bases represent?
The effective Hamiltonian is I showed was the real space expression. So if you actually want to calculate the electron structure, you need to expand this to the momentum space. So as you can see from this expression, the K states in one layer interacts with the K plus G1 states in another layer. Did I make it clear? And for example, this function makes the K states in one layer interacts with the K plus G1 plus G2 states in another layer.
Yeah, if we have two layers, basically you have like upper layer A and B atoms and lower layer A prime B prime atoms. So like those atomic bases does not actually correspond exactly to this 2x2 model.
Could you say that again?
I mean, if we have two layers, upper layer has A and B atoms, two atoms. Lower atoms also have A and B atoms. So basically, if it's not rotated, we have like 4 bases, right? So normally it is represented by 4x4 matrix. So in this case, we have 2x2 matrix. I'm wondering if there's any one-to-one correspondence, like I mean, this 2x2 matrix, it has some bases. So like, does it have any correspondence to those?
This is a 4x4 form. So H1 is 2x2 and H2 is 2x2. And here I plot, I showed this in the basis of layer 1 A and B and layer 2 A and B. So that I should have shown this clearly.
Thank you.
Okay, so share. Let's move it to Okay, so I'll skip the one of singularity, suppression of Dirac point shift, and actually I did this before. I worked on twisted Moire graphene because of this topic. So I was very curious how the energy spectrum of such large unit cell looks like on the magnetic field. We know that each graphene shows Landau level, but if we apply magnetic field, we know I showed that unit cell of Moire pattern, there are AA-like region and AB-like region, but the Landau level of AA-like region looks completely different from the Landau level of AB. So I was very curious how the nature connects them on the magnetic field. And I calculated it, and it shows the very beautiful Hofstadter's butterfly pattern. Actually, Hofstadter's butterfly in a usual conventional material occurs at unfeasibly large magnetic field of 10 to the 1,000 Tesla. But since this is very large unit cell, it shows the butterfly at very feasible, not very, but it's a feasible magnetic field length. This, it's now very, people accept this as granted, but at that time, it was not sure whether this Moire superlattice can act as an actual potential for electrons. For example, long time ago, 20 years ago, the Moire pattern usually observed in a STM image, but they consider it as avoidable or some kind of artifact that might not affect the physical properties. But now we know that the Moire pattern actually affects the electronic structure and can be used to design the physical properties. And in collaboration with the experimental group, we show the first full span of Hofstadter's butterfly. And in collaboration with the experimental group, we show the mapping of twisted angle in the magic angle twisted by graphene. And so far, I showed the twisted by graphene, where the Moire pattern comes from the rotational fold. But we can also make this Moire pattern by stacking two layers with a different period, such as graphene on boron nitride. And here again, I show that the effective method can clearly describe the physical properties observed in experiment. And it shows why the mini Dirac point in the conduction band is shows much smaller spacing than that in the valence band, and lift of belly degeneracy, and so on. And I also worked on a carbon nanotube. Carbon nanotube is single sheet of carbon rolled up into cylinders. The chiral vector, the roll up direction determines the physical properties. It seems that it's running out of time. So I will skip very, so here I show the lattice structure of
excuse me, we still have enough time since there were also discussions, so don't worry.
Okay, so here I show the lattice structure of single wall and double wall carbon nanotube. Although the difference between single and double wall nanotube is just the number of tube, but this little small difference makes the calculation of double wall nanotube very challenging. This is because single wall nanotube always have an exact periodicity. So we can calculate the Bloch equation and get the electronic structure. But double wall nanotube, in most cases, the period of inner and outer tube do not match. So we cannot define exact periodicity. So we cannot solve the Bloch equation. This is the reason why, although almost 30 years passed since the first discovery of a multi-wall nanotube, but very few is known about its electronic structure. However, we could successfully describe the electronic structure by describing this as moiré superlattice. And this is twisted by graphene, which is described by rotation angle. This is graphene on boron nitride, which is described by rotation and isotropic extension. Double wall nanotube is interesting because it is a combination of rotation and uniaxial expansion due to its geometry. Uniaxial expansion compared to the other two-dimensional system acts as some kind of a strain, uniaxial strain. That makes a very extreme situation compared to other two constants. For example, we can make this metallic structure by the combination of two semiconducting nanotube, or with a combination of semiconducting nanotube and metallic nanotube, we can even make a very discretized level structure, even in the absence of magnetic field.
Professor Moon, we have another question from Sung Jong. Please, Sung Jong.
Is there any, before going to that like nanotube stuff, is there any qualitative difference between boron nitride, graphene superlattice, and graphene rotated superlattice?
Yes, there is interesting practice. So boron nitride, the on-site energy of boron nitride is far from graphene. So the charge neutrality point of graphene is not strongly affected by boron nitride. However, it's still affected by the Moire superlattice. So we only see single graphene bands, but affected by boron nitride. But what is more important is that boron nitride breaks the inversion symmetry of graphene. The Dirac point of graphene is protected by the inversion symmetry of graphene. So if we can break it, we can open a gap. We actually showed this, but the opening is very small, just 0.3 milli-electron volt at the main Dirac point. However, the opening is quite large. At the main Dirac point is just 0.3 milli-electron volt, but here it's on order of 0.1 electron volt. If we do not break the inversion symmetry, these points are also protected. But since the inversion symmetry is broken, they leave the degeneracy. So that's
Actually,
the main.
yeah, actually, my main question is a little bit different from that view, because I'm actually wondering, like, the difference between graphene and graph boron nitride is one is rotated, the other one is the lattice mismatch, right? So, like, without mentioning the gap of boron nitride or the like inverse symmetry breaking of boron nitride, still they have some difference in terms of the some kind of mismatch. So if, for example, like if we have graphene bilayer graphene, and maybe artificially if we apply isotropic strain on only one of those two graphene layers, then still it has inversion symmetry and like it doesn't have AB energy gap, but it can, I think it can also develop more pattern, right? But not by rotating it. So if
Yes.
we artificially do it, then is there going to be any difference or similarity between those two systems?
Still, the boron nitride has a potential difference, on-site potential difference between the two sublattices, and the graphene keeps the same on-site potential. So inversion symmetry is conserved. So actually, whether the presence of gap is the main difference. Otherwise, they look almost the same, except that twisted bilayer graphene have two Dirac bands. Actually, considering the other belly, there will be 4 Dirac bands near the charge neutrality point, compared to the 2 Dirac cone of graphene and boron nitride. So, except that there would be no clear or no meaningful difference.
I see. Okay, thank you.
Okay, so that's the end of carbon nanotube, and yeah, we will move to the quasi-crystal. So many people worked on a low-angle twisted bilayer graphene, which clearly develops a long-range Moire period, and Hamiltonian is clearly periodic. But recently, we showed that 30-degree stack of 2 hexagonal lattices can make a dodecagonal, 12-fold rotational symmetric quasi-crystal. So what is quasi-crystal? Quasi-crystal is a unique state which is ordered but not periodic. It is at the interface between periodic crystal and amorphous solid. So it may provide some useful insight into the effects of atomic ordering. Although quasi-crystal is very rare in nature, but we show that we can design and fabricate quasi-crystal by stacking atomic layers at a specific configuration. For example, if we stack 2 layers of a hexagonal structure in a 30 degree, then we can get 12-fold rotational symmetry. Or if we stack, for example, 2 layers of a square lattice on a 45 degree, then we will get 8-fold rotational symmetry. And this is the RPS angle resolved photon emission spectral image. And the red and blue hexagon shows the first brilliant zone of each graphene layer. Unlike the periodic Moire pattern at other angle, we can see infinitely many scattering spots, which is not periodic in a momentum space. And at the same time, people in the Tsinghua University also observed a similar peak. They showed this main peak. Okay, how can we calculate the electronic structure of such non-periodic system? So we cannot rely on the conventional Bloch theorem. It is well known that the interlayer interaction of incommensurate atomic layer are described by generalized Unclug scattering condition. The K states in layer 1 and K tilde states in layer 2 interacts when they satisfy the Unclug scattering condition. This is nothing but the momentum conservation. Here G and G tilde stands for the reciprocal lattice vector of each layer. In a conventional Moire superlattice, we have a periodicity, so the Hamiltonian spanned from K0 are spanned in a periodic and overlapped pattern. The layer 1 and layer 2 bases are overlapped. But there are infinitely many other incommensurate atomic layers which cannot be suitably described by a single Moire period. For example, some system does not have Moire periodicity. Some systems have more than 2 different periodicity. So I developed a generalized theoretical model which does not rely on Moire period. So the idea is simple. We want to find the K and K tilde, the subspace spanned by the Hamiltonian, satisfying the Unclug condition. The K0 state in layer 1 is scattered to K tilde states, every K tilde states which satisfy this condition. And this K tilde is scattered back to K and scatters back to K layer 2, layer 1, and again. If you see the form of these spaces, you can see that they are clearly described in this way. However, we only need a subset of these bases. This is because the Brillouin zone of each layer is translationally invariant with respect to its own reciprocal lattice vector. In other words, K and K plus G is equivalent in layer 1. But please note that they are not equivalent in layer 2. From this, we can simplify the subspace in this way. And K in layer 1 is spanned by the reciprocal lattice vector of layer 2 and vice versa in the expanded Brillouin zone. So regularly spaced, it means periodically spaced. So Moire superlattice, the subspace spanned by the Moire superlattice is periodic in the momentum space, but the generalized model, the points are spanned by the primitive lattice vector of the opposite layer. So they do not overlap to the same point. Actually, this can be applied to more general configuration. And if we apply this to the scattering RPS-like pattern, we can see that the Dirac point of either layer are spanned to periodic pattern in the extended Brillouin zone. However, since layer 1 and layer 2 are incommensurate, they are mapped to distinct point in the first Brillouin zone. And this is consistent with the experimentally observed RPS pattern. So how the interaction Hamiltonian looks like? To get better visual image, we will move to one-dimensional tight binding chain. In a real space, the interaction between two states are described by the distance between the atoms. In a momentum space, the interaction between K states and K tilde states are described by the Unclug condition. And I show that in the choice of the subspace, my subspace, the first layer states are expanded by the spanned by the layer 2 reciprocal lattice vector, and second layer states are spanned by the reciprocal lattice vector of layer 1. And the interaction between these two states are given by the Fourier transform of the transform integral at this wave vector. It's not quite intuitive what this wave vector stands for. However, if we rotate, invert k tilde with respect to k naught and define new axis, then we can see that the interlayer hopping is described by the wave vector difference. This means that we could convert the tight binding model in a momentum real space to tight binding like model in a momentum space. So it depends on the distance. Okay, so if this is a tight binding like model, what is the merit of converting the real space model to momentum space? There actually is. In a real space model, to describe the incommensurate system, we need infinitely many atomic bases. However, in a momentum space, we can save a lot. In a momentum space, the interlayer return to the real space. In a real space, we are using atomic orbital as basis. So intralayer hopping and interlayer hopping are all described by the hopping between different atomic orbitals. So although their intensity magnitudes are different, but mathematically we cannot distinguish intralayer hopping from interlayer hopping. In a momentum space method, however, the interlayer hopping is just the interlayer hopping, but intralayer hopping now appears as the diagonal component of Hamiltonian, which acts like the potential in the momentum space. So we can clearly distinguish them. And we know that in a van der Waals system, the potential, say the bandwidth, is much larger than the interlayer hopping. So interlayer hopping acts perturbatively. This reminds us the Aubry-André model in a real space. There, when the perturbation is weak and incommensurate, the wave function is localized to real space. Likewise, in our model, the wave functions are localized in momentum space, which means that the states related to one of the k points are all localized. The space spanned from k are all localized to finite range. So we can just choose, we do not need to choose infinitely many points, many k points to calculate the eigenenergy. Instead, we just need a finite number of states within the sufficiently long k-space cutoff and get the electronic structure at that point. By plotting them as a function of k naught, we can get the quasi-energy band structure even in a system in the absence of periodicity. Okay, so let's take a look at the electronic structure. Before we take a look at the electronic structure of quasicrystal, let's briefly review the electronic structure of a conventional twisted bigraphene Moire superlattice.
Professor Moon, excuse me, there is a question from Alexei.
Yeah, sorry, I just wanted to confirm one simple thing. So essentially the dual tight binding model works because individually the layers are periodic structures. Is that correct?
Could you say it again?
I mean, this dual tight binding model that you were describing, it works precisely because individual layers are periodic systems.
Exactly. So this system.
Yeah, but they are, well, they are rotated at an angle that doesn't create a periodic superstructure, but say if the layers themselves were not periodic, then this dual tight binding model would not be helpful. Say if you just took two quasicrystals, two-dimensional quasicrystals, and just rotated them one with respect to the other, then this would be of probably of no help. Okay.
You are right. The question is, so this works because each layer still keeps the periodicity. So this is a quasicrystal composed of periodic lattice, but yeah, it cannot work on a quasicrystal composed of two quasicrystalline layer. So yeah, that's right. So each layer is quasicrystal, then we will need another method.
Okay, thank you.
Okay, so low angle twisted bilayer graphene. As I showed in the previous section, and as Seongjong asked, the interlayer interaction has a 3 wave vector component. So one state in layer 1 interacts with the 3 states in another layer, but their K points would be different. As you already learned in our textbook, quantum mechanics textbook, the interaction between 2 different states becomes stronger as the interaction strength, for example, transfer integral increases, and as the energy difference decreases, okay, as the resonance occurs. At most wave vector, the energy of layer 1 is very different from the energy of these 3 states in layer 2. That's the reason why the most part of twisted bilayer graphene band structure are almost decoupled. It just looks like the monolayer graphene. But a specific wave vector happen to be one state in layer 1 becomes very close to the energy of another layer 2. Then they strongly interact and makes a band opening, such as a saddle point Van Hoff singularity and some kind of flat band structure. Okay, how about graphene quasicrystal? In this specific configuration, I found that there is a very specific condition where one state in layer 1 equally and strongly interacts with 2 states in layer 2. And these states also interact with 2 states in layer 1. And they makes a 12-fold the resonant ring. So it makes a 1D-like chain Hamiltonian. This is very unique feature in this specific configuration. And actually, that's these 12 points satisfy the resonant condition. As you can see from the distance from the Dirac point, so 0 point is distance of this from the Dirac point, and 7 point is distance of this from the Dirac point of blue layer. So these 12 points have the same energy. And the dashed line is the interaction path, but all of them are one of the reciprocal lattice vector of each layer. So they satisfy the momentum matching condition, and they are degenerate. So they make a very strong interaction. I calculate the density of states and plot the density of state of decoupled bilayer graphene as well. We can see very sharp density of state, Van Hoff singularity at these energies. This is nothing but the extension of the conventional Moire superlattice feature, but these 12 states shows the Van Hoff singularity arising from the quasicrystalline states. And we can easily develop the Hamiltonian by using 12 states with 2 sublattices. And since the 12 waves strongly influence couples with each other, increasing the number of bases does not make noticeable. Actually, it's noticeable, but does not make a dramatic change. So 12 waves interacts most strongly. Here I plot the band dispersion, and the 12 Dirac cone gathers at specific point and makes hybridized to make a new band dispersion at specific point, some flat band or Mexican head-like structure, and so on. And yeah, how the electron distribution looks like. At most other energies, since graphene does not allow localization, electrons are uniformly distributed over the entire space. This is a real space map. But at these quasicrystalline states, electrons are localized to specific points in the unit cell, or only at specific points. So it makes quite not long. It does not have any periodicity. So it makes a quite unique pattern, quasi-crystalline pattern. Quasicrystal does not have periodicity, but it still has order. We can map the entire space with a highly ordered manner. This is one of such methods, which is based on the vertex configuration. And quasicrystal shows inflation. Instead of a periodicity, it shows some kind of fractal scaling property. We can map the space with fractal inflation, and this pattern is consistent with what we observed in our experimental STM image. And this pattern is consistent with the electron probability distribution as well. Note that this red line and black line shows I'm sorry, it's quite difficult to show the pointer. This red line and black line shows the first order and third order inflation map of the quasicrystalline tiling. They consistent with the actual electron distribution. It should be noted that such long range order of quasicrystal is broken with even a small deviation of angle. So unlike the conventional quasicrystal, which all the atomic positions are intrinsically arranged in a quasicrystalline order, this van der Waals quasicrystal can be considered as an extrinsic quasicrystal, where the entire system is composed of a pair of perfect crystals, but the quasi-periodicity occurs from the interaction between the layers. This means that yeah.
Excuse me, Alexei has a question or comment.
Mm-hmm.
Yeah, I'm just curious. I'm not sure that's true in all contexts, but I believe, at least for some quasicrystals, there's basically a statement that they correspond to taking a higher dimensional periodic structure and just cutting it with an incommensurate plane. This distinction you're now making doesn't seem that, I mean, seem to be blurred to me. So can you comment on that?
So yeah, actually the definition of quasicrystal is a little gray area in condensed matter. Of course, some will not agree with me, but long ago, not very long ago, even 10 years ago, people defined the quasicrystal as some atomic arrangement which has the rotational order which is not allowed in a periodic configuration, such as the 5-fold rotation or 8-fold rotation or 12-fold rotation. For example, in that definition, there will be no 3-fold rotational quasicrystal or 4-fold rotational quasicrystal or 6-fold rotational quasicrystal, because those rotation angles can be consistent with the periodicity. However, now I think it's not the major definition. We found, I'll show very briefly, I found the 4-fold rotational symmetric quasicrystalline states, and several people already reported the not in this graphene quasicrystal system, already showed there can be 4-fold rotational quasicrystal, 6-fold rotational symmetry, and so on, such as researchers like Sokola and so on. Okay, so there is another definition of quasicrystal, which view the n-dimensional quasicrystal as a projection of higher dimensional periodic crystal. This is, yeah, this is okay, but for example, the Fibonacci crystal can be considered as the projection of two-dimensional periodic crystal. One-dimensional Fibonacci crystal can be considered as two-dimensional projection of two-dimensional periodic pattern. However, there is some artificial point there. There will be some acceptable window parameter. That's, I don't think it's not very physical. So I found, I tried to find some paper research whether this higher dimensional picture can benefit the electronic structure calculation. Say, if we can calculate the electronic structure of a two-dimensional quasicrystal by using the electronic structure of four-dimensional crystal, but I couldn't find any. The higher dimensional picture is only, so far, as far as my best knowledge, it's useful only to describe the geometry. So it's almost rather than mathematical interest. And I haven't seen any electronic structure related matters. So anyway, so it's quite difficult to define whether this is quasicrystal or something like that. But at least it's ordered. Yeah. I'm sorry. If you ask why this, how can you prove this is ordered, then I cannot answer very clearly. But it looks like it's ordered because it's composed of just 12 waves. So it's ordered wave. So what I prefer as a definition of quasicrystal is the general. I think it's widely accepted definition. The quasicrystal is a system which is described by the basis of which number is larger than its dimension. For example, these two. So it looks similar to your question. The higher dimensional, the projection of higher dimensional objects. But in this definition, we do not need any projection. We just use 4 bases in a two-dimensional space. That's all. We do not need any projection, and just 4 independent bases would be enough to describe this quasicrystalline pattern. I don't know whether I could answer your question, or do you have any?
No, that's perfect. You even answered the question that I wanted to ask afterwards, precisely whether this projection method could be somehow could help to compute the electronic structure. But
yeah, I couldn't find that. So actually in the long term, I would like to find because quantum Hall effects or higher dimensional quantum Hall effects, I would like to find some interesting insight from that picture, but yeah, so far I couldn't find it. Maybe that would be my long-term goal. I don't know whether it is feasible or not. But thank you for pointing this. Okay, so this is extrinsic quasicrystal, which means that the quasicrystal order arises from the interaction between the layer. What's the main difference? In an intrinsic quasicrystal, we cannot control the quasi-periodicity. But in a van der Waals quasicrystal, we may switch on and off the quasicrystal by, for example, making the interlayer interaction stronger, weaker, or since the interaction is based on the resonance, we may break the resonance by changing the on-site potential, for example, by applying electric field and so on. So yeah, it allows us to tune the quasicrystalline, switch on and off the quasicrystalline states. And very recently, actually, I'm just liking this, but very recently I found where I tried to generalize these quasicrystalline states, I happened to find this four-fold rotational quasicrystalline states in the twisted biographene quasicrystal. It's very beautiful that the lattice structure is 12-fold symmetry, but this electron structure actually has a 4-fold symmetry, and it does not have any periodicity. So yeah, it's of course quasicrystal does not have any application yet, but physically and mathematically, I'm enjoying this topic. So the conclusion is we can design electron structure by controlling the lattice registry and controlling the interaction paths in the system. And thank you for your attention.
Thank you, Professor Moon, for this very interesting talk. So we have time for questions. Sergey?
Yeah, I have a question. I think you mentioned this at the very end, but I'm not sure whether I understood it. So what is there a technology, and if there is, what is the technology of, so to say, changing these angles continuously in an experiment? Can you say a few words about that?
Yeah, now the experimentalists are doing almost magic-like work. So they can put it, of course, they cannot exactly tune it, but at least they can control the rotation angle by the resolution of 0.5 degree.
And how do
because graphene has an edge structure, so they prefer either armchair edge or zigzag edge. So you can easily see from the optical microscope. First, they put one graphene layer to some polymer, transparent polymer, and prepare another pair in the bottom. And by using the optical microscope, they rotate and put it. This allows them to.
But then it's fixed, right?
Yeah, it sticks. Then it sticks.
You cannot change the angle in the experiment.
It's possible, actually. So far it was not possible. But people, I think in Corridin in Columbia University, they made some kind of notch or knob in the upper layer graphene, and by using the STM, not STM, AFM tip as the pointer, and just drag and rotate it. So it's not feasible for the engineering or more the mass production, but it's still very good for experimental, the pure scientific experiment. Because the interlayer interaction is very weak, so they can easily just put AFM and just rotate it.
A second question. These Moire pattern are kind of approximately periodic, as you explained, but the truth is that they are again quasi-periodic by themselves. I mean, something is not; it cannot be exactly periodic, right? Because the starting point is that the system is not periodic anymore. So there is some kind. Is there some kind of Moire pattern on top of a Moire pattern, and so on and so forth? And what would that mean? Or is there any physical reason why we should follow that up, or is that becoming some kind of mathematical stuff?
Actually, so I visited IBS, I think more than 6 or 5 years ago, and at the time I met a professor named Greenwood from Australia. So he asked me this, whether So if we can make the moire of moire, for example, stacking atomic layers at 5 degrees and stacking 12 layers, then it will make some.
No, I didn't mean that. I just meant the following. If you take a bilayer system and you produce some moire pattern, great. So what I'm saying is that this moire periodicity is actually only approximate periodic.
Yes.
So therefore, again, in the same system, there should be some, maybe some way to define a Moire periodicity of these Moire patterns, so to say. Does it make sense or not? So I'm not going to stack more, in my thoughts, more layers on top. I just say that the same thing should, again, since it's anyway not periodic, so I have a way to identify some period of an almost periodic pattern. But then, since it's not exactly periodic, again, maybe on a different scale, I will see another even larger.
It's not. Actually, I have some. No. Actually, it's not exactly periodic in terms of atomic position, but in the momentum space, in the wave space, the periodicity. The real space periodicity does not matter. Only the difference of wave vector matters. This is the physics of beat of wave. The beat of wave of F1 frequency, F2 frequency make a beat. So it's a very general phenomena. And in the momentum space, we can clearly, exactly define the periodicity. The extra periodicity would be F1 plus F2 over 2 and F1 minus F2 over 2. This difference part, F1 minus F2, usually makes a long periodicity in the real space. That's the exact periodicity. And since we can describe the electronic structure both in the real space and momentum space, we prefer momentum space. And in the momentum space, we can define the moment, the delta K, the wave vector defines the Moire periodicity very strictly, very clearly. So this is, although we cannot, this is consistent with what I showed in the previous, the real space image. So although it is not atomistically exact periodicity, but this is the exact periodicity that electron feels.
Okay, thank you.
We have question from Alexei. Alexei, please.
Yeah, actually, I have several questions. So one is actually related exactly to the figure that's presently shared. So because you have this fractal inflation, so can you use that somehow to develop some sort of RG for these quasicrystals?
Develop what? Could you?
Renormalization group, because you have some sort of self-similarity.
Yeah.
Actually,
the Franco Nori long time ago did some kind of renormalization group approach to calculate the Fibonacci structure. I tried to apply this, but it was not very feasible at the time. I'm sorry, I do not remember why, but the renormalization group approach wouldn't work, or maybe I quitted that approach because I found much better, much clearly described this model. But anyway, in a previous 1980s or 1990s, Franco Nori did this in a simple one-dimensional Fibonacci crystal. But in this structure, I had, at this point, I have no plan yet.
Okay, and the second question is actually related to the discussion how one defines a quasicrystal. So you mentioned that one possible definition is by saying that that's a structure which simply has a larger basis than, that the number of basis vectors is larger than the dimension of the space. Again, I'm curious whether, well, coming back to the electronic band calculation, could you then not try to play the same game you played with the twisted layers? Because now you can basically split the bases into two groups, both presumably or maybe more, so that in every group you basically have periodic structure with a number of basis vectors smaller than the dimension. So you have crystals, and then perhaps do a perturbation theory in between them.
Could you say the question part again?
Well, I'm just curious how, I mean, if one accepts the definition of a quasicrystal as a set of points where the number of basis vectors is larger than the dimension, what I'm saying is that do you think it would make sense to compute it, then use that definition to try and compute the band structure simply by decomposing the basis into several parts where you can compute the band structure because it's completely periodic, and then introducing the coupling between the two, and then maybe using the same ideas that you used for the dual tight binding model?
Actually, I used that idea. So I used the periodic basis in each layer and just introduce the interaction between them. So
yeah, right.
the main.
Yeah, but my point is precisely that with this definition of a quasicrystal, then it seems like perhaps a very universal recipe how you can compute an electronic structure of any quasicrystal, so long as you identify this extended basis.
You mean the not only this extrinsic quasicrystal and try to apply to intrinsic quasicrystal. Actually, I thought about this, but I couldn't find it. And I think this is doable, but I just kept in a to-do list. But this to do this, we need. So here we rely some feature. So it's possible. It's possible, but. Here the calculation becomes easier because of the fact that because the interlayer interaction is much.
Well, of course, you have to do some sort of perturbation theory, I suspect.
Right. Yeah, but in a actual, for example, intrinsic conventional quasicrystal, there is no such perturbation or the strength difference. That, in that case, real space approach and momentum space approach does not have any clear difference. So we need infinitely many bases. So there is no clear, how can I say it? So some criterion that we can cut off the basis. So I'm very curious to see, it's still in the to-do list.
Okay.
Yeah, thank you for that interesting pointing there.
Do we have any further questions?
Can I ask a question?
Yes, please.
Thank you for interesting talk. Can you comment on the effect of magnetic field? I mean, Hofstadter butterfly in graphene quasicrystal?
I'm doing, actually, I calculated everything 3 years ago and still writing the paper. But I found another interesting features. So I put priority to those part. But anyway, so this, I cannot state very clearly, but the graphene quasicrystal in on the magnetic field have a multiple area scale. So the Landau level or Hofstadter's butterfly depends on the area it fills, the electron fields. So the reason why we see such fractal Landau level structure is that the electron fills different periodicity or different area scale in the momentum space, in the real space. Quasicrystal have a much more different the area scale. So we see some interesting the overlap of different area scale, or actually it is area, but I think it's much convenient to say the energy structure is depends on different length scale. So we expect some kind of overlap of Landau level structure. But one point, so it's not directly related to your question, but one point, one drawback, one disadvantage of Hofstadter butterfly in graphene quasicrystal is that the interesting feature arises at this high energy, plus minus 1.5 electron volt. This is quite large electron volt energy to access by using the conventional transport measurements. So we are now, in collaboration with the other colleagues in KIAS, we are doing some better way to see such coupling phenomena at much feasible electron density.
Thank you.
So I'm sorry, I didn't made it clear. This low energy resin is almost unaffected by the quasi-crystalline potential. As you can see, it's just the pristine Dirac cone. This is because the wave states at this point do not satisfy the momentum conservation conditions. So they do not effectively couple each other. So this is almost decoupled range.
Okay, do we have any further questions?
Yeah, can I ask a question?
Yes, please.
Oh, okay, hi. Can you hear me?
Yeah.
Okay. Other than such a beautiful repeating pattern in different scale of in real space, so you have this repeating pattern for different length scale, and I really appreciate it. It's beautiful. Do you have other than geometric such repeating patterns? Do you have a physical response also showing that pattern at different scales?
Yeah, that would be the most, what I, the most often, the most frequently observed phenomena related to different length scale would be the magnetic phenomena. So that usually happen in this Hofstadter's butterfly of this quasi-crystalline states, but that's quite large energy and quite many electron density, large electron density. So although we can show the interesting property at this range, but that would not be very clearly observed. Instead, it's not related. It's not 100% related to different length scale, but I found that the optical selection rule clearly reflects the rotational symmetry. So we can define the angular momentum or angular quantum number of these states, as I showed in the number in the light panel. But for light circularly polarized light and left circularly polarized light, it clearly changed the angle, allows the transition that changed the angular momentum by ±1. I could analytically show this, and now preparing a paper on that. So that would be the physical quantity that shows the rotational order of quasicrystal. For the different length scale or inflation pattern, yeah, I have no other idea other than the magnetic response.
So for the optical responses, that's no momentum transfer arising. It's like from one K to the other K. The K, there's no momentum transfer.
Yeah, there is no momentum transfer. But actually, this is this K naught point. Wait a moment. As I showed in this figure, since the upper layer and lower layer are incommensurate, one K point in one layer corresponds to various points in another layer. Actually, this image shows the Dirac point, the matching point, the points matches to the Dirac point of another layer. You can see since the 2 points are incommensurate, there arise infinitely many, so incommensurate pattern. If this is periodic, then the pattern also appears in a periodic way. But this is incommensurate, so we expect infinitely many points. This means that the quasicrystalline band structure or the optical transition may occur at various wave vector. Of course, the contribution of each wave vector are different. So if we can see distinguish the optical transition from this point and this point, then there would be difference in the magnitude. But that usually cannot be observed in experiment, I guess.
Okay, thank you.
I have another question related to the previous, like the Hofstadter's butterfly question. I think, I mean, in your previous work, the Hofstadter's butterfly could be measured because the wavelength becomes quite big, because I mean, due to that generated large lattice, more pattern. But if you go into that the quasicrystal regime, then it's the direction toward short wavelength, right? Short, more pattern. So I'm wondering if there's anything still left, which was reminiscent of that. What is it?
No, actually.
So it should be gone, right?
So we cannot see the Hofstadter's, the Hofstadter's butterfly. If we say it by the broadening of Landau level to band structure, then we cannot see such broadening in the low magnetic field regime of quasicrystal, because as you said, the area scale is very small compared to the Moire, the longer period. Instead, we just see the overlap of different Landau level centered at different band edges.
Okay. Thank you.
Can I ask one more question? How did you calculate the effective magnetic field in quasicrystal? I mean, how did you include the effective magnetic field?
Yeah, that's the point. So actually, I calculated at the time when I calculate the Hofstadter's butterfly of quasicrystal 3 years ago, I didn't develop the effective model of quasicrystal yet. So I calculate the energy spectrum by using quasicrystal approximant. Approximant is a periodic structure of which local atomic configuration looks quite similar to the actual quasicrystal. We can find many quasicrystal approximant near 30 degree. For example, 29.8 degree can make a periodic structure with a longer periodicity. Then we can define the period and calculate the Hofstadter's butterfly. In this way, we cannot calculate the butterfly of 30 degree, but we can calculate the butterfly of 29 degree, 29.5 degree, and up to 29.98 degree. And they are all consistent with each other. And actually, there is some interesting part, but I will let you know after I write the paper. Otherwise, my colleagues will kill me. Anyway, so So I cannot 100% guarantee that this structure is exactly same as this Hofstadter's butterfly is exactly same as the butterfly of 30 degree, but there wouldn't be no qualitative difference. I expect, as we can expect from the effective model in the absence of a magnetic field. However, I'm trying to, so this year I'm quite busy, but I'm planning to develop the magnetic field model, magnetic Bloch band model by using this effective model in the absence of magnetic field. In that way, if possible, so I'm just have a very naive idea. So I'm not sure whether it is possible or not. But if this is possible, then we can calculate the Hofstadter's butterfly, exact butterfly of graphene quasicrystal.
Thank you.
Thank you.
Okay, thank you, Professor Moon, for this wonderful talk. So let's thank our speaker again.
Thank you very much.
So with this, we conclude